Okay, hello calculons, welcome back. So we're going to learn about a new topic today called differentiability, and this is a new term. So we're going to say a function is differentiable, and this is a property that a function can have. So we'll say a function is differentiable, meaning able to be differentiated. At some point, if two conditions are true about f of x. One, f of x is continuous. So if something is differentiable, just right off the top, you know it also must be continuous. That's just kind of a given as part of that definition. And two, the derivative f prime of x exists at that point. And remember, when we talk about a derivative, basically we're saying that the limit as h goes to 0 of your f of x plus h, or whatever form you use of this quotient, is equal to 0. So these are our two things. If something is differentiable, it must be continuous, and the derivative at that point exists. And that's how we should think about this. So let's talk about what this looks like on a graph. So some things that are differentiable are functions that you're familiar with, right? Like a line. If you think of a line, it's a continuous function. If you look at any given point, you can take a derivative. Same with like a parabola or like something with some shoot-whoops or whatever. You know, a sine graph. These are things where the derivative always exists at any given point. They're continuous functions. Now, if something is not differentiable, there are a couple ways that it can look. So if it is not differentiable. One is it can satisfy or cannot satisfy the first condition, right? It might also be not continuous. So you could have a jump in a function. If we have a jump, we obviously can't find a derivative at that point. Same with a hole. We can't find a tangent line at that point that doesn't exist, or an asymptote or something like that. So if it's not continuous, you know it's not differentiable. But the new case today that we also want to think about is what's happening if it is continuous but not differentiable. And of course, if it's continuous but not differentiable, what that means then is that f prime does not exist. So f prime doesn't exist. And the word that I use for this is it's called a sharp corner. And we see a sharp corner in something like an absolute value of x. And, so if you have, for example, a sharp corner, like at this point, you can't really draw a tangent line. And like f prime doesn't exist, not just because you can't draw a tangent line, but also because the slope approaches different values on both sides. If it was a parabola, it like approaches 0 on both sides. But in this case, at that sharp corner, the slope is approaching different values on each side. You might also see something like a shark fin. So the shark fin is another case. We have a sharp corner where the slope is approaching two different things from the left and the right side. So these functions are continuous, but they're not differentiable. So look out for that sharp corner. That's something we definitely want to be aware of. Okay, so that's one thing we want to talk about. What does it mean to be continuous but not differentiable? What does a differentiable function look like? One of the only questions you'll kind of see about this is you might see, for example, f equals 3x when x is less than 0, and then e to the 2x minus 1 if x is greater than or equal to 0. And the question I might ask is f of x differentiable at x equals 0? Well, you need to check the two things, right? You need to first off check, is it continuous? And then does f prime exist? And with f prime existing, we mean that f prime is the same on both sides as well. Okay, so is it continuous? First off, let's take a look at that. So if something is continuous, remember that means that f of 0 must equal the limit as x approaches 0 of that function. So we're going to look from both sides. Okay, so f of 0 is the bottom case. So that is e to the 0 minus 1, which is 0. Okay, now if I take a left-hand limit here, the left hand, if I take the limit as x approaches 0 from the negative side, I end up getting 3 times 0, which is 0. If I take a limit from the right side, take the limit as x approaches 0 from the right side of f, I get e to the 0 minus 1, which is still 0. Okay, so this is our check that we know it's continuous. We've done that maybe like a month ago. Now when we want to check, does f prime exist? Is f prime the same on both sides? I'm going to find f prime on both sides. So I'm going to find the derivative of each of these. So the derivative of 3x is 3. The derivative of e to the 2x is e to the 2x times 2. So from the left side, if we take the limit as x approaches 0 from the left side of f prime, we just get 3, right? But as we take the limit on the right side, as we approach x goes to 0 from the positive side of your f prime, that's using this bottom equation right here. So that's using the bottom, so that just goes to 2e to the 0, which is 2. So what we say here is these f prime limits, the f prime does not match on the left and the right. And because that f prime does not match on the left and the right, that means that that f prime doesn't exist, so this is not a differentiable function. It has to be continuous and the derivative has to be the same in order to make that work. So this is a case where you'd have like a slope of 3 and then you go to a slope of 2. So you'd still have like a sharp corner at that point, even though it's a continuous function. So that's why it's not differentiable. Let's look at one more case like this. Suppose I tell you f equals 2x plus 1 if my x value is greater than or equal to 1, and then x squared plus 2 if your x is less than 1. Okay, so we're going to check if it's continuous first, so we're going to check f, and then we're going to check, does f prime exist, meaning, let's use proper grammar, does f prime exist, and is it the same on both sides? Okay. So let's look at continuity. If we look on the left side, the limit is x goes to 1 from the left side. I get 1 plus 2, that's 3. If I take the limit as x goes to 1 from the right side, I get 2 times 1 plus 1, which is 3. Great. So it's continuous, right? F works on both sides. And let's take a look at the derivative, though. So my f prime here is equal to 2 and then 2x. For my values here. So if I take a look at the left hand, if I take a limit as x goes to 1 from the negative side of my derivative, that's 2 times 1. Again, I'm just taking these limit. I'm like plugging in the x equals 1 value to both sides. So there I get 2. If I take a limit from the right side here, that is obviously equal to 2 because that's just this case. Okay, great. So in this case, because this is continuous and because that f prime is the same on both sides, that's a clear indication that this is indeed a differentiable function. Okay, great. So that's what you're doing, right? It needs to be continuous and that derivative needs to exist, be the same on both sides. Okay, so that's what the word differentiable means. Thanks for watching. I'll see you guys soon.